Hi, I'm Rasan Abulev, and today I will be presenting fully convolutional one-stage detection with future pyramid networks. Anchor, box, Anchor boxes are often used in many detectors in the computer vision field. They are predefined reference boxes with different size and aspect ratio placed over every point in future maps of images created for convolutional neural network. They are used as references for the model to predict the target boxes with respect to them. More clearly, the model first finds if the anchor box references the target box which has an object. And if they do with a regression, we find the distance between the anchor boxes and the target box and predict to locate the target boxes. They are used in pretty much every state-of-the-art models like Fast and Faster RCNN, most YOLO versions, RetinaNet, and SSD. But anchor boxes are not without drawbacks. Firstly, since require many hyperparameters like scales and aspect ratios and EU thresholds, since as we use EU to see if they have an object inside them, this extra hyperparameter tuning is time consuming, and so is computing overlaps of hundreds of thousands of anchor boxes. Also, since anchor boxes have a fixed shapes, they cannot recognize unusual shapes and have to be tuned for hyperparameters to get good at recognizing these shapes. Our main idea with FCOS is to eliminate the dependency on the anchor boxes. Instead, we treat every pixel inside the ground truth box as positive sample and we find where the bounding box is with respect to that point. We show that this per pixel approach removes anchors and also achieves even better accuracy than most models that use them. We take each point on a feature map created by feature pyramid networks and then map them to the original image. If that pixel is within a ground truth box, we label it as a positive and compute the distance from that point to the locations of the edges of the box and find the class of the object. Our model predicts these models and then we use the given loss function to train our model to better predict these values. Here T star is the target bounding box coordinates and C is if the pixel is within a ground truth box. Here, as you can see, you can see our models backbone is a convolutional neural network. Like for example, in this paper, ResNet is used in this paper's experiments. After going through the backbone, we feed the future pyramid network to get different future maps for features with various sizes to detect objects with different sizes. We get future maps P5 from C5, P4 from C4 with the addition of upsize P5 and P3 the same way. P6 and P7 are produced by downsizing their bottom value. Then we apply convolutions to these future maps we get to get classification and regression sentence heads. These are models predictions. If a pixel is within two ground truth boxes, there may be some ambiguity. When that happens, we assign it to a smaller box. But that may not be true. This FPN, we reduce this case significantly from 23 to 7% because in FPN, different sizes of future maps are used for objects with different sizes. Now we also predict centerness, which is used to find how close a point is to the center of the object, so that we give these points higher scores. And the points at the edge of the boxes are given lower scores. So we get higher quality bounding boxes, which account for more important center points. From the results, we see that FCS outperforms other methods with anchor boxes on almost all cases. Here the AP refers to average precision. This tells how accurate the model is. And APS means precision with small objects and APL means precision with large objects. FCS can also be used as a region proposal network to provide other models with reference boxes. AR means average recall, which means how good the model is at finding ground truth boxes. We see in this figure that without centers, many low-quality boxes with low IO get a high classification score. But when you use centerness, only high-quality boxes are found. Now we see that we can achieve a high anchor-free, proposal-free detector with one stage that performs at least as good as other state-of-the-art models. But since they are without anchors, they have smaller capacity and also have no hyper parameter tuning problems, and they cannot be used effectively to propose regions other than just use anchors. But the model has also have problems. With small or overlapping object, models still may not be able to correctly assign the overlapping pixels, causing inaccuracy. Since we predict for every pixel in objects across 5 scales, there is still a high computation cost. Also, not as high as anchors. Additionally, even with centerness, we can get low quality boxes since we account for every pixel. Thank you for listening to my presentation.